In this video lecture, we're going to discuss AVL trees. What is an AVL tree? An AVL tree is a binary tree wherein it is a balanced search tree. It was created by Adelson, Velsky, and Landis. So how could we consider a binary tree as an AVL tree? So it is based on the valence factor. It is the relationship between the height of the left subtree to the height of the right subtree. The value should be 1, 0, or -1. So on the next slides, I'm going to discuss what is a valence factor, how could we determine the valence factor, so that we could determine if if the given binary tree is an AVL tree. But before we discuss further about AVL tree, let's have a review about binary search tree. So let's start with the binary tree definition. If say binary tree, the child node of a parent node should not exceed by 2. The maximum is 2 child per parent node. So it could have none, 1, or 2 child. And in binary search tree, the root node defines which is the lower value and the higher value on the array. So for example, the root node here is 10. So in the tree, all on the left side will be less than 10. All on the right side of 10 will be greater than 10. Okay, so based on that logic, if we're going to search for a certain value, by checking the relationship, we could determine if we're going to go to the left or the right child of the parent node. Okay, so for example, we're going to search for 18. So we're going to start comparing 18 to the root node, which is 10. So 10 is less than 18. So therefore, we're going to go to the right child of 10, which is 15. Compare it with 18, it's still less than 18. So therefore, we're going to go to the right side of right child of 15, which is 17. 17 less than 18, still it's not equal to 18, and we haven't found 18. 17 is less than, so we go to the next child node, which is 18. So compare, and it's equal. Therefore, we found the value. Okay, so that's how binary search tree works. We determine if it's less than, go to the right. If it's greater than, go to the left. Okay, if the node is greater, go to the left. If the node is less than, go to the right. Okay, so how many steps in finding 18 in our tree? So based on this, it is based on height. So 1, 2, 3, 4. We have 4 steps. So therefore, the O notation for this type of binary tree is O at H. Okay, let's have another example of binary tree. Now let's have a scoot to the left. So if say scoot to the left, all of the nodes are connected on the left side of each parent node. So let's search for 5. Same as with the previous slide, we're going to compare it with the parent node, starting with the root node. So 10 is greater than 5. So therefore, we're going to go to the left child node, which is 8, and compare it with 5. Still, 8 is greater than 5. So therefore, we go to the next node, next child node, which is 7. Compare with 5. It is greater than, and we haven't found 5. So we proceed with the next child node, so which is 6. So it's still greater than 5. So let's proceed with the next child, which is 5. So 5 is equal to 5. Therefore, we found the value that we are searching for. So now, how many steps? Same as with the previous slide, it is based on height. But as you can see in this type of binary search tree, Height is the same as the number of nodes. So therefore, in this type of binary tree, if we have lots of nodes, for example, we have 100 nodes, and if it's skewed to the left, it means we're going to do searching for 100 steps if it's on the last node. Okay, so that is the worst case scenario. So that's why the big O is O at n. Okay, another example, skewed to the right. So we're going to search for 14. And again, compare the value on the parent node and then go to the child node. So 10 less than 14, go to the right. 11 less than 14, go to the right. 12 less than 14, still go to the right. 13 less than 14, go to the right child. And 14 is equal to 14. We found the value 14. So how many steps again? It is based on height. So number of elements is equal to the height. So 5 steps. So therefore, the worst case scenario in this type of tree is big O at n. So comparing the 3 or 2 scenario, so skewed to the right or skewed to the left, or this type of binary tree, which is faster, which is more ideal when we are searching a certain value? The first or the second? Based on our computation, both are based on height. But in skewed to the left or to the skewed to the right, height is equal to the number of nodes, the number of elements in our binary tree. But here, it is not dependent on the number of nodes. It is just based on height. So therefore, this kind of binary tree is more ideal when we are searching a certain value. So therefore, this is faster, and this concept is actually used in an AVL tree. Okay. So as much as possible, the left side and the right side should be equal so that it will be faster. It will be more convenient to us in searching a certain value. Okay. So why AVL3? Again, to minimize the worst case scenario. Ordinary binary tree, the worst case scenario is O at n, if it's skewed to the left or skewed to the right. But in AVL3, instead of O at n, it could be either big O at height or O log n. So which is faster compared with the big O at n. And again, n is the number of elements or number of nodes, while h is height of the tree. Okay? So now, how do we determine the valence factor of a certain binary tree? So the formula for the valence factor is height of left subtree minus height of right subtree. Let's have this example. This binary tree would have 4 nodes. So let's define first the height of the left subtree. So let's start with the childmost node, which is this. So we start it with 0. We count it starting with 0. Then when we go up, so you increase it by 1. So 1, 2, 3. So it means the height of the left subtree is 3. And since we don't have a right subtree, so the valence factor will be 3 minus 0 is equal to 3. So based on this computation, if it's positive, if the valence factor is positive, it means it's skewed to the left. Okay? Another example. Now we have 3 nodes. So again, childmost node. So let's count 0, 1, and 2. And we don't have a height for the right subtree. Therefore, the valence factor will be 2 minus 0 is equal to 2. Again, the valence factor is positive. Therefore, it's skewed to the left. And for the 2 node, so So 0, 1, balance factor, 1 minus 0, since we don't have right sub 3, so that's why it's 0 for the height of the right sub 3. So the balance factor is 1. And in case if there is no child in a node, so the balance factor will be 0 minus 0 is equal to 0. And if a child is connected on the right, okay, so it means this will be considered as your right sub 3. Okay, so 0, 1, balance factor, we don't have a left sub 3. So 0 minus 1 is equal to negative 1. As you can see here, if the balance factor is negative, the binary tree is skewed to the right. Okay. Another example, 3 nodes. So 0, 1, 2. Balance factor, we don't have a left sub 3. 0 minus 2 is equal to negative 2. Again, the balance factor is negative, therefore it is skewed to the right. Last example. So 0, 1, 2, 3. Balance factor, 0 for the height of the left sub 3 minus 3 is equal to negative 3. Okay, so that's how we determine the balance factor. Height of the left minus height of the right sub 3. So if you still remember, on my previous slide, what is the AVL3 acceptable balance factor? It is 1, 0, and negative 1. All nodes in a binary tree should have this balance factor, negative 1, 0, and 1. Let's have an example. Okay, let's determine if this binary tree is an AVL tree. Again, each node should have a balance factor, negative 1, 0, or 1 only. So let's check the height first. For 8, it's 0, and then it's 1 for the left side. And for the right side, 15, 0, and then 10 is 1. So for 8, node 8, balance factor will be 0 minus 0 is equal to 0. While for node 15, since we don't have a child node, so same as with 8, 0 minus 0 is equal to 0. But for node 10, we have 2 child. Okay, so balance factor, height of the left minus height of the right. So 1 minus 1 is equal to 0. Since all balance factor is equivalent to 0, therefore, this is an AVL3. Okay, another example. Let's check if all balance factor of each node is equivalent to negative 1, 0, or 1. So let's start with 7. So balance factor of 7. So 0 minus 0 is equal to 0. While for 8, we have a left 3. So 1 minus 0. So we have 1. For 10, so we have 2 nodes connected to 10. 2 child on the left side. So 2 minus 1 is still equal to 1. While for node 15, so 0 minus 0 is equal to 0. And let's expect the value of BF, 0, 1, 1, 0. So all are acceptable. Therefore, this is an AVL3. Okay. Again, the balance factor should be either negative 1, 0, or 1 for all nodes to be considered as an AVL3. Another example. So we have now 5 nodes. So 0, 1, 2, 3 for the left side, and for the right side we have 1. So let's check if each balance factor is 0, negative 1, or 1. Let's start with node 6. Balance factor, 0 minus 0 is equal to 0. For 7, node 7, left is 1, right is 0, so 1 minus 0 is 1. How about node 8? So we have 2 on the left, but none on the right. So 2 minus 0 is 2. How about node 10? So we have 3 minus 1, 3 on the left, 1 on the right. So we have 2. And for 15, so 0 minus 0. So as you can see, the balance factor, some balance factor is not equivalent to -1 or 0 or 1. Therefore, this is not an AVL3. But there are ways to convert this type of binary tree to be an AVL3. So we're going to discuss it on the next video lecture. Thank you for listening. See you on the next video lecture. Thank you.